Hello everyone, this is a chapter of the CSM16A content team called Public Resources, and we're using this team, or actually using is not a great verb, we're building this team so that we can help you clarify some frequent misconceptions we have seen when we were teaching in CSM about E16 a couple of semesters ago as well as now. And this public resource is also serving to introduce you to the resources we provide as CSM. Alright, so with that all aside, in the last public resource we were talking about power, which is the rate at which a circuit uses energy. And we learned about the difference between dissipating power and supplying power, and how to determine whether circuit components supply or dissipate power. If you want to check that video, you can check my channel, which probably has the public resource video up already. It's called Public Resource 05. But this is Public Resource 06, and today the topic is not power, but we're going to talk about equivalent circuits. So, for everything you learn in 16A and 16B, we teach these circuit things for a reason. There's always a motivation to learn about this, or else there will be no meaning in teaching these circuit things to you. So what is the motivation of equivalent circuits? Well, before we talk about the motivation, let's try to define equivalence of circuits first, because circuits are not mathematical objects where we can just call equal. So circuits are equivalent if they have the same IV relationship. When we talk about IV relationship, including during lectures, if you remember lectures exist, what we'd say in lecture is that IV relationship is the current voltage relationship within the circuit. When we say current voltage relationship of a circuit, we mean the proportion at which current and voltage passes through a circuit. So, for example, let me give you 3 circuits here that I will use to motivate you learn about equivalent circuit and to introduce the concept of equivalent circuit. This upside down triangle means ground node. Some people write it like this, some people use the 3 horizontal line instead. For me, I like the triangle sign a little better because it helps me make the recording faster and present information to you faster. But during exam, please write the 3 horizontal line until you go to a class that uses a triangle. Okay, so that's the left circuit, and I have 2 more circuits to draw here. And I have one last circuit I'd like to draw, which is a little different. It's with a current source now. And I'm changing my resistor as well to 1 ohm. Okay, so now I'm introducing you to these 3 circuits, and let's talk about the IV relationship of these circuits. So in the left circuit, we see that the voltage passing through the entire circuit was 2 volts. And the current passing through the entire circuit was, well, we're going to use Ohm's law here, so 2 volts divided by 1 ohm is equal to 1 amp. So the general IV relationship is that the proportion or the ratio at which voltage passes against current is equal to 1. Is equal to 2. So the ratio is 2. So for every 2 volts that passes through, actually this should be 2 ampere. So for every volt that passes through, for every 2 volt that passes through the circuit, 2 amperes of current are produced, which means the IV relationship is actually 1. Okay, now let's look at the second circuit. The circuit uses 4 volts instead, and the current across this is now 2 amp, because 2 amp times 2 ohm is equal to 4 volts. So the IV relationship for this then is actually equal to 2 instead of 1. So we can say that these two circuits are not equivalent because they have a different IV relationship. Okay, what about the third one we have here? So it has 2 ohms, and the resistor is, it has 2 ampere, and the resistor is 1 ohm. So the voltage passing through this circuit is 2V. So, sorry about this. So we see that the IV relationship would also be still equal to 1, which would make these two circuits equivalent because they have the same IV characteristic, or the same IV relationship. Okay. A slightly more intuitive example would be if I just directly create another copy of this circuit on the left, but everything is scaled such that for 1 volt I have for 1 voltage I have 1 ampere unit of current flowing through the circuit. Then I will still have a circuit of IV relationship 1. So what I was trying to say here by showing you these 3 circuits is that there are circuits that may look very different from each other, but has the same properties in terms of having the same IV relationship, and we call these equivalent circuits. But there are also circuits that might look very alike, but have different properties in terms of IV relationship, so they're not equivalent circuits. Okay, so that's a little fun thing about circuits. So, if you don't mind, I will now move on to talking about something else, which is, well, now we're presented some very simple circuits here to talk about equivalent relationships. But what if we have some super complicated circuits? So I'm going to write a not so complicated circuit, but still show you a complicated enough circuit. So the circuit I'm going to show you is as follows. Where I have 2 resistors in parallel and I have 2 terminals. Notice that AB here is an open circuit. So having AB here doesn't really influence the circuit. Okay, so what if today I have this kind of circuit? It's a little confusing to analyze, right? So what the equivalent circuit really is about is to create simpler versions of circuits that have the same IV relationship. And if we can do that, then we can save a lot of work in computation, because then we can be working on simpler versions of this current circuit. And that will save us quite a lot of time. So let's talk about how to do it. There are 2 general ways, or 2 general simple versions that we can put circuit structures in. The first version is called Thevenin equivalent. So this is where nouns from lecture are going to start coming back. So if we're working with the Thevenin equivalent, then we're going to simplify the structure, simplify the original circuit into the following structure. So once again, let's remind ourselves that to have equivalent circuit is to have a simpler version of a circuit that has the same IV relationship, so we can save calculation. So so intuitively, or as we would want to put it for simplifying computation, we want to have a simple version to water down a circuit into, so that it's easier to compute simple versions of circuits, right? Because if actually, it's faster to show you what the Thevenin equivalent really looks like. So namely, for any circuit, I'm going to find another circuit which has one voltage source and one resistor, respectively VTH, Vthevenin, and RTH, Rthevenin, that has the same property or same IV relationship as the previous. So, in other words, to make a Thevenin equivalent version of this super complicated circuit above, what I need to do is I need to find a version of this Thevenin version circuit that has only VTH and RTH, but still has the same IV relationship with the above circuit. So how do we really do that? Well, we can do this algorithmically, and I will be using the way that your lecture notes suggest, which is usually how we do it. I cannot spell English words, oh my god. Okay, so the algorithm for finding a Thevenin equivalent is to first find VTH by measuring the voltage between A and B in the original circuit. So in other words, I'm going to try to measure the voltage between A and B here, these two terminals, so that I can later determine what is VTH. And then I will need to find another thing that we're missing in the prototype, which is RTH. And I can find RTH by first zeroing out the source, any independent sources in the circuit, and then I try to find equivalent resistance between A and B. This stands for equivalent resistance. So it will probably be helpful to give you an example now. So I have this original circuit here that is, once again, pretty complicated. And it actually has a name called current divider. But this is not in scope for the public source. We'll talk about current divider in another chance. But I'm going to do some MVA with this circuit so that I can find VTH and RTH. So first of all, I need to find that... Oh my god, this is super huge pen. Okay. Oops. So first I find that VAB is equal to, once again, Ohm's law. IS times the parallel of R1 and R2, right? So the parallel of R1 and R2, I can just write it like this, or more formally, I can write it as IS times R1, R2 over R1 plus R2, and that's just how parallel resistors can be calculated. This comes from the fact of this being equal to the equivalent resistance of parallel resistor, which follows the form as written below here. Okay, so now we have found VAB and we'll use it as VTH. Then now I need to find RTH, right? Because that's the second step of my algorithm. So to find RTH, what I need to do is to find the equivalent resistance between A, B by zeroing out all sources. So I'm going to draw another version of the above circuit, but every source is zeroed. First of all, if a current source is zeroed, then it cannot provide any current, so it provides zero current, which means it becomes an open source. Sorry, not open source, open circuit. Resistors stay the same. So the equivalent resistance between A and B is then still the parallel between R1 and R2. So RTH is equal to R1 parallel R2, which is equal to, once again, the expression we have here above. So therefore, the Thevenin equivalent of this circuit becomes what I will write here with my original pen. And that is, once again, I have a voltage source here, VTH is equal to what I have before, which is IS R1 R2 over R1 plus R2. And I have a Thevenin resistor here, which is equal to RTH 1 R2 over R1 plus R2. Alright, nicely done. And then I will just draw the terminal back here. Okay. This terminal is pretty useful because that means we can connect anything to this terminal. So the application is the application works like this. If I connect another circuit to the terminal I have in the Thevenin equivalent, it's equivalent of putting another circuit in between the original terminal of A and B. So it's pretty convenient in the way that we have simplified one part of a complicated circuit, such that we have simplified the current divider part of this originally complicated circuit. Imagine here's another complicated circuit. So we simplify one part of the complicated circuit into this form, so that it's easier to calculate for the entire calculation of this loaded with another circuit. So once again, we simplify one part of the original circuit so it's easier to compute things later. Okay, so that's one way of finding equivalent, and this is called Thevenin equivalent. Alright, there was a cut in between, but now that we have finished talking about Thevenin equivalent, it's now time to talk about Norton equivalent. So the Norton equivalent circuit works very similarly to the previous Thevenin equivalent that we talked about, which is about simplifying a circuit into the simple structure of, well, not necessarily simple, but simple enough for us to simplify a lot of computation. And the structure looks like this. It is very similar. Oh my god, I can't speak English today. It is very similar to the Thevenin version of equivalent, which is that we have a current source, and this time we have a resistor in parallel with the current source. So once again, our goal is to find a circuit that works exactly with the exact same IV relationship, such that this version of the circuit has the same IV relationship with the complicated circuit that I had here, but was gone for some reason. Let me fix that up. I don't know why the circuit was gone. It was kind of mysterious. Okay, but now that I have put the circuit back in place, let's copy this into where it belongs. So once again, I'm going to try to find a simple version like the Norton equivalent that has the exact same IV relationship with this, so that I can simplify some computations later when I'm analyzing some kind of complicated circuits like this that I have above, where it's this original circuit composition with another circuit. So once again, there's an algorithm for finding Thevenin equivalent. So similarly, there's also an algorithm for finding a Norton equivalent. First step is very similar to find the Norton equivalent, and you do this by measuring or calculating for the current. Well, in this case, we'll be calculating, but measuring the current between the original node A and B. When there is a short circuit between A and B. So here's the catch. When we're calculating for Thevenin, we care about voltage, and we are measuring the voltage across an open circuit, but when we're talking about short circuit, when we're talking about Norton equivalent, we care about current, and we are measuring the current by putting a short circuit into the original circuit. So we're editing the circuit. Second step of the algorithm is to find R and O, or the Norton equivalent resistance, which is the same way you find the Thevenin resistance. So I'll not explain second step again because we have explained it during the Thevenin process. But to find I and O then, I'll have to make some variation of my original circuit by putting a short circuit between A and B. And that is going to change the circuit quite a little. I will end up with a circuit that looks something like this. Well, so there's still R1 and R2. But now I have a short circuit between A and B, which I'm going to put right before the terminal. So what happens then is that all of the current IS flows through the short circuit, and there will be no current flowing through R1 and R2. This means I and O is equal to IS. And furthermore, we already know that R and O, which is the Norton equivalent resistance, is equal to R Thevenin, which is equal to R1 parallel R2. So my Norton equivalent of the original circuit would then be something like what I'm drawing here. And I have my original terminals here. And you can see the resemblance between a circuit based on a current source and its Norton equivalent. Alright, so now that we have talked about these concepts, let's move on to the exam question walkthrough part of this. Right, and let's separate this into two different clips so it's easier for you to watch.